putting a margin and picking a maximum, basically to stop the back propagation, right? Okay, so okay, if I can go 5 more minutes, then this topic, you have 5 more minutes? Okay, okay. So at least we'll be able to make progress with this topic. So anyway, now let's take a look and do the partial L over partial W. Okay, so suppose that's our goal. We want to determine the weights that will make this contrastive loss as less as possible for both similar cases and dissimilar cases. So let's start with the similar case. Okay, in the similar case, the expected output is what? 0. Okay, so if y is 0, what will happen to the dissimilar term? Disappears. If this is 0, what does this become?
Half x.
Right? So then, as you can see, partial L over partial W. So I should have kept that picture. Let me just quickly put this picture. Here's a CNN. Here's some kind of distance, some kind of a vector. Then this is A1, this is A2. This is our loss, and this is our L, and this is our contrastive loss. Okay, so basically there are some weights involved over here, weights involved over here. So we wanted to see how do we train this partial L over partial W is always our goal, right? So wouldn't that be equal to, let's say, partial L over K of dW? Okay, so this is our dW over here, the distance between the two. Okay, so partial L over dW times partial dW over partial W. Okay, so how do we define dW? If this is A1, this is A2. A1 is a function of weights, A2 is a function of weight. So dW could be defined as
A1 squared.
A1 of I, yeah, exactly. So I'm just saying it's a function of the weights minus A2 of I W over all the outputs. If the output size is 30, we'll do a summation on 30, right? And square it, and then square root. Because that's the definition of a distance, right? Okay. A small point over here. Could I have written it like this? dW equal to A1 of W minus A2 of W square root. Sorry. Is this the same as this?
No.
Then you might say, oh, cancel the square and the square root, right? See, it's like if I gave you 2 points, x1, y1, x2, y2, right? 2 points. How do we measure the distance? Isn't it x1 minus x2 square plus
y2 minus y1
2 square root?
square root.
Does the square and the square root cancel? They don't. So that's why I put it individually for each I. Like if I don't put it for each I, you'll say, oh, square root cancels. Okay. Anyway, so this is not the right way to write the distance formula. Okay, so now let's take a look over here. So tell me what will be partial L over partial dW, or sorry, partial dW.
Yeah, dW. Nothing but half raised to 1/2.
So y was 0, right? So this is half dW squared. So what is this? Derivative with respect to
just dW. Right?
just dW.
Yeah.
Okay, now let's go to the second part. Partial dW over partial weights.
Weight. That
Okay.
is
So now I want to take the derivative with respect, because both of these outputs are function of the weights, right?
yeah,
So wouldn't this be
half.
half exactly,
A1 of W
the
minus,
whole summation,
Yeah.
A1 of I of W minus A2 of I of W
raised to 3
square, right? Then whole thing, because square root is half, right?
Half, yeah.
So this will be
Minus
minus half. The
yeah.
half is what I brought it over here. Okay, then further multiplied by
derivative of inside.
partial over partial W of the inside, which is summation A1 of I of W minus A2 of I of W square. You guys agree?
Mhm.
Okay. What is this inner part over here? This part over here.
1 upon square root.
It's dw.
It's dW. Right? Because this will be 1 over this
Yeah, 1
whole thing
upon
half, which is the definition of the dW. So isn't this 1 over 2 dW? Right? Now let me further take the derivative of this. Won't this be, so this 2 comes out over here.
2 times A1 of
So summation A1 of I of W minus A2 of I of W, right? Further multiplied by partial over partial W, A1 of IW minus partial over partial W, A2I. You guys agree?
2 cancel.
2 cancels. Now let's put it in the whole term, partial L over partial W. Remember this term was
dW.
dW. So if I multiply this with this, what will happen?
Cancel.
So partial L over partial W. As you can see, dW cancels.
Simply the summation on
So summation A1I of W minus A2I of W times partial over partial W A1 of I of W minus partial A2I of W over partial W. And there should be a summation over here. So this is our very, very interesting result. Let me show you why. So this will tell us how will we train the network. Okay, so let's sidetrack for a second. Okay, forget the contrastive loss, right? Okay, let's say I'm given a regular neural network. Some weights are going in. This is my sum. This is my activation function. This is my output. This is my loss. Okay. How do we write partial L over partial W for a regular neural network? Isn't this
half
partial
y
L over partial A
yeah,
times
partially over
A over S times partial
S over partial W.
S over partial W, right? What do we call this part?
Delta.
Delta. Okay, so let me erase this part.
So we have delta.
Okay, so suppose this was like a mean squared loss, just to give you a quick idea. Then wouldn't this be half yi minus ai square and the summation over
Yeah.
all the outputs? Okay, so what will be partial L over partial A then?
Minus of y minus.
minus yi minus ai, correct? Okay, so that means this partial L over partial W will look like this, minus yi minus ai, right?
Delta.
Times
Delta.
the derivative of the activation times partial S over partial W. So now compare this with this answer.
What is the loss? Yeah.
So do you see like there's, or let me write it as partial over partial W, whatever that S is. So do you see over here, there's a partial over partial W. So if I rewrite it, one this be A1 of I of W, A2I of W. You guys agree? Right? And then further, let's put this term over here too. Summation A1I of W minus A2I of W. So can you guess what this is then? Compare this to this.
So it's kind of
Instead of accepted value,
loss, it
this
is
is
Wasn't this the delta basically? Right? For a regular neural network. Then further, we go backwards and do the further gradients. Okay, so so essentially what this is telling us is that the gradient over here is nothing but, well, sorry, I shouldn't call it gradient, I should call it the delta. So what I'm saying is the delta over here is what?
derivative of loss into activation.
No, see this part over here, treat it as a delta.
So the distance between.
So delta is basically this minus this. Whatever this vector was minus this vector gives us a delta over here. Then we can just back propagate this delta. I don't know if it made sense or not. But, so all I'm saying is to train, okay, maybe this will explain. Okay, so what I'm trying to show you is how to train Siamese networks. So what we do is, we don't create in reality two different networks. In reality, we just have one network. We feed in image 1. Whatever A1 is, we store it. Okay, now we feed in image 2. Suppose we call this A2 now. Okay, so once we feed in image 1, we don't do any back propagation. Once we feed in image 2, whatever output it produced, now we will do the back propagation. Because remember, the purpose is if our I1, I2 similar. If we already know they are similar, right? Then obviously we want to train the network using this technique. So take a look over here. What will we do then? What will be the delta over here?
A1 minus A2.
That's what it's saying. That will be A1 minus A2, right? So then, let's pretend when we did the forward pass, there were some gradients due to I1. When we did the second image, there were gradients due to I2. So what is this saying now?
The first gradient minus the second gradient.
Second gradient, and then we update the kernels and whatever based on that. Okay. So I'll go over it one more time. I've only shown you a similar case, but gradually, like I said, it's like once we know how to train the network, we don't focus so much, okay, how will we do this? Really, it comes down to is coming up with interesting loss functions to control the behavior. Because like I said, once we have a loss function, if we can get up to this point and we know what the deltas are here, rest is the same, okay? In this particular case, there will be like a difference of the gradients involved, okay? So you guys will actually program it and you'll see what a good job it does on face recognition as an example. Okay. All right, so this week's assignment, like I said, is high priority for you guys to finish the CNN, because this one will use that CNN that you build to further put it in assignees, and next time I'll show you triplet and quadruple and all those other advanced networks.